Hey guys, this video is going to go over verifying trig identities, and this is on page 6 of your packet. This is a little bit different if you were to compare it to simplifying trig identities, and really it's only different because now you have to actually prove that one side of your equation equals the other. So now you have an equal to sign and you do have two sides of your equation. So just a couple of things that I've highlighted up here for you if you want to just take note of that. It does kind of walk you through a couple of things if you're not really sure how to get started. Go ahead and take a look at this, but one of the most important things is that you want to work on one side and then make sure that it gives you the other side. So what you'll see me do a lot is I'll work on the left side because usually that is a more complicated side, the left side is, and then I'll prove that it actually ends up being the right side. So I won't touch the right side at all. And I'll just kind of at the end prove that the left side does come out to simplify and give you the left side. I'm sorry, the right side. And then the other thing that I want to really emphasize is always try something, because I know a lot of times you look at something and you don't know where to start. Well, just kind of dissect it one thing at a time and see how can you simplify something so that it ends up giving you the right side. So now what's kind of nice is, if you were to compare it back to simplifying equation or the identities, these, because you're verifying, you have a goal to work towards. You know what you're trying to get to. So now just keeping that goal in mind, it might be a little bit simpler, a little bit easier to actually change or manipulate some identities. So let's go ahead and get right into it. Number one, you have that entire fraction and you want at the end for it to just be 1. You want to show that at the end it equals 1. So I'm going to take one piece at a time. I have my numerator, which actually, if you look at it, you have sine squared plus cos squared. Well, if you know your identities really well, that is actually your exact identity, which all just simplifies to give you 1. If you're not sure where I got that from, go ahead and pause the video and look back at your actual identities and see if you can gather that. So now I know that the numerator is 1. The denominator is still, for right now, cos squared of x times secant squared of x, and I want it to equal 1. So you'll see me kind of repeat the right side over and over again. Okay, so now this is a fraction, so now let me look at what's left over. I have cos squared and secant squared. Well, secant squared I know is 1 over cos squared. Now if I change that to 1 over cos squared, it helps me tremendously. So I'm going to write that as 1 over cos squared of x, and secant of x I'm going to write as 1 over cos squared. And the reason why I'm doing that is because I can technically put that cos squared that's already there over 1 and cancel, leaving me with a 1 at the bottom, 1 at the top. So 1 divided by 1 is simply 1. And there we go. We've proved that that does come out to be what we needed it to be. So this little box that's filled in here, that literally means that I have demonstrated what I needed to demonstrate. So you'll see me do that a lot too. It's kind of like, showing that I'm done with my proof. Okay, number 2, again, I'm going to attack the left side. I want to simplify as much as I can here so that I end up getting the right side. Now this one's rather, it's lengthy. It's a lengthy process. Because I don't have any identities that I can use right away, I'm going to try to force it so that we can somehow use an identity in here, because if you take a look at your goal, you want it to be 2 cosecant squared. That cosecant squared tells you that we're going to have to somehow incorporate a Pythagorean identity in here. So if I look at my denominators, I know they're very close to my Pythagorean identities, but they're not quite there yet. So the first one I have 1 minus cos, the other one I have 1 plus cos. The only way I can get these two fractions to become 1 is by getting a common denominator first. So to do that, I'm going to multiply my first fraction, top and bottom, by the other denominator, 1 plus cos of x. And I'm going to multiply my second fraction by the first denominator, which is 1 minus cos of x. Cos of x. So now when I do that in my first fraction, of course I have 1 plus cos of x at the top. At the bottom, once I FOIL these, because I will have to FOIL these two binomials, once I FOIL that, I will end up with 1 minus cos squared of x. Go ahead and pause the video now if you need to work through that and just to verify. The second fraction is going to give you 1 minus cos of x, and at the bottom, again, you'll have 1 minus cos squared of x. Okay, so now I have a common denominator. My common denominator is 1 over cos squared of x. At the top, though, I have 1 plus cos plus 1 minus cos. So 1 plus cos plus 1 minus cos. So if you look through that at the top, there is something that you can cancel. The coses do go ahead and cancel, and you end up with 2 at the top, which is good. We're getting close to our goal. Now at the bottom, 1 minus cosine squared is actually from your identity. So see if you can look back at your Pythagorean identity, somehow rewrite one of them so that it gives you 1 minus cosine squared. And if you do, you should end up rewriting that as sine squared of x. And again, we're very close to our goal. There's only one more step left. To show that 2 over sine squared equals 2 cosecant squared, all I have to do is see that this is technically 2 times 1 over sine squared. So I'm separating it so that it's more obvious that 1 over sine squared is simply 2 that's already there. 1 over sine squared is simply cosecant squared, and we've just proved it. Oops. And there you go. Okay. Number 3. So you may think that you'll have to FOIL this, and actually you can. It will work. However, there's a simpler way. So again, if you think back to your Pythagorean identities, you can write secant squared minus 1 simply as tan squared. Again, if you're not sure where that's coming from, check back in your identities and see if you can manipulate the one that has secant in it to get you what you need. Okay? And then sine squared minus 1, same thing, comes straight from your identity. If you were to rewrite that identity, you would end up with cosine squared. And I need to show that it equals negative sine squared. So now let me see, I have tan squared now and I have cos squared. Well, the cos squared I can't really do anything to simplify, but the tan squared I know is sine squared over cos squared. So there's that. Now the cos is just going to be what it was. And the reason that I did that is because now, if you take a look, you're multiplying these two fractions. I can put this cos over 1 and cancel the coses because they are diagonal to each other. Which is nice because now all you have remaining is sine squared of x. And actually there's one little thing that I just caught, and it's actually a very common mistake, as you can see. But at the top on number 3, the sine squared minus 1, actually if you were to rewrite the identity, it should give you a negative cos squared. Sorry, it should be a negative cos. So this is also negative. And so when you multiply sine squared times a negative 1, it gives you that negative at the very end. And so that gives us what we needed on the right side, which is negative sine squared of x. And there you go. Number 4. So I'm going to attack the left side because the right side it looks very simplified. So I already have the sine, or the second part of the left side is just sine by itself. The first part is cosecant. So I know cosecant is 1 over sine. So let me write that down. 1 over sine of x minus the sine that's already there. So now let me go ahead and put that sine over 1 and see what I can do to put those two fractions together. And as you know, the only way you can do that is if you have a common denominator. So let me get a common denominator of sine on this one. So multiply top and bottom by sine. And so I have 1 over sine of x, just like it was. Second fraction becomes sine squared of x over sine of x. So now I have a common denominator, and so I can keep that common denominator, and let's see what we have at the top. I have 1 minus sine squared. 1 minus sine squared, again, comes straight from your identity, and if you rewrite it, it becomes cos squared of x. So really, what I need to do, remember, look back at your goal every single time. I need to expand this a little bit because at the top I have two cosines technically. Those are two cosines. So let me write them out separately so maybe that'll become a little bit easier to spot out. So I have two cosines really over sine of x. Okay, I want it to be cos times cotangent. So what I'm going to do here then is notice that there's only one term in the denominator and there's two terms at the top. So what I can do is actually kind of use the or split it up like that so that I'm focusing on cos over sine just like this. And if I do that, then I can write that piece of it simply as what cos over sine would be, which is cotangent of x. And then I have the cosine of x still there. So cosine of x times cotan of x gives you what you needed, cos of x times cotan of x. And you're done. Number 5. Now that one's kind of similar. Number 5, I'm going to work with the left side. I'm going to rewrite everything that I can in terms of sine and cos because as you can see I have no squares in here at all, so I cannot use my Pythagorean identities, at least not now. So I'm going to rewrite this as, or cosecant I know is 1 over sine of x. I know cotangent is cos over sine. And if you take a look at that, you already have your common denominator, which is really nice, so we don't have to do that. So really I can keep my common denominator, which is sine of x, and add the top, so 1 plus cos of x, just like that. Now I need, at the end, I need to have almost like the flipped version of that, and of course that plus should be a minus, but I do need a 1 minus cos at the bottom. Now the only way I can get that to happen is I'm going to have to multiply by the reciprocal of my I'm going to have to multiply by the conjugate of the numerator because the conjugate of that numerator is exactly what that is. So 1 minus cosine of x. Top and bottom I'll do this. So then at the top, once I multiply those through at the top, I'll have to actually FOIL. Once I do that, I end up with 1 minus cos squared of x. And at the bottom, I get the sine of x that was already there times the 1 minus cos of x. Now I'm going to leave that still in parentheses for right now because I want to focus on some other things. Now, if you take a look at the top, you have 1 minus cos squared, and all of a sudden you have that identity that you can use. So really 1 minus cos squared is really just sine squared of x. And of course you have that entire denominator still there. Now, luckily, because I did not distribute that sign in right here in this step, it becomes really nice here because now what I can do, because you have in the denominator sine times that factor, that binomial, I can actually simplify vertically. So because technically I have 2 signs at the top, 1 at the bottom, so that 1 sign at the bottom cancels with one of the ones at the top, leaving you with sine of x at the top and 1 minus cos of x at the bottom, just like you needed. Number 6. So again, the left side, I'm going to let's actually look through. So at the bottom, I have 1 plus secant of x. That looks very close to your identity, but not quite. And the biggest problem with the denominator, other than the sign, but the other big problem is that it's not squared. So we know we can't really work with the denominator right now. The top, though, is tan squared, and I know tan squared has an identity, and if you rewrite tan squared, it would be secant squared minus 1. And let me keep the bottom the same. Now the reason why I did that is because, like we did in class the other day, secant squared minus 1 is actually a difference of 2 squares. which you're right, it does factor. So secant squared minus 1 is really factored to secant of x minus 1 and secant of x plus 1 over the 1 plus secant of x that's already there. So now, luckily, these two factors, my two addition factors, do cancel entirely. They do cancel. And so what's left is secant of x minus 1. And it's kind of a bummer because it's not quite what we needed to get at the end. So what I'm going to have to do, because as you can see, my goal, or my right side of the equation, is all in terms of cos. So let me kind of try to get that here. So if I rewrite secant as in terms of cos, I know it's 1 over cos. And maybe I can write, because I know it's going to end up being two fractions, let me just go ahead and attack that now. Let me go ahead and get a common denominator now. So I'm going to write 1 as cos over cos, because really, it's still 1. So now I have a common denominator. I don't have to worry about that anymore. So now if I put those two fractions together into 1, my common denominator is cos of x. The tops then just come together to give you 1 minus cos of x, which is exactly what I wanted. Number 7 looks like a lot of work, but it's actually a lot simpler than you might think. Now this one, the very simplified side is the left side. So on this one, I'm going to actually simplify the right. I'm going to work with the right side. Okay, so now if I look through it, I have tangent times secant squared minus tangent. Very close to an identity, but not quite there yet. So what I'm going to do is notice that I have two terms, and they both have one tangent in it. So because they both have one tangent in it, let me go ahead and pull it out as a GCF. So I'm going to pull out tangent of x, leaving me with secant of x squared in the first term, and in the second term, if I take a tan out of tan, I'm left with a simple 1. Now if you take a look at that, secant squared minus 1 is actually straight from your identity, which becomes tan squared. So now you have tan times tan squared, which gives you tan cubed of x, and that's exactly what we wanted. There we go. And lastly, number 8 does kind of work similarly. Now what I'm going to do on this one, again, the left side is the part that's simplified. I'm going to work with the right side. So again, in parentheses, I have a lot going on, so I'm going to simplify. I'm going to rewrite that. So now I'm going to ignore, for right now, I'm just going to ignore that cosine that's there at the end. I'm going to ignore it. So let's work with what's in parentheses. I have 4 sines minus 6 sines, right? So, and I'm saying that so that you can kind of see what they both have at most. They both have at most 4 sines, or in other words, sine to the 4th power. So I'm gonna do almost what I did here, where I pulled out a GCF. I'm gonna use the same idea there. So I'm gonna pull out from here sine to the 4th from each of those, leaving me with, let's see, 1 sine to the 4th. If I take sine to the 4th out of sine to 4th, sine to the 4th out of sine to the 4th, I end up with 1. If I take sine of the 4th out of sine to the 6th, I end up with 2 remaining. So sine squared. And I'm just so I don't forget it later, I'm just going to pull that one down. I'm not going to really look at it, but I'm just going to pull it down with me right now. So now I have that sine to the 4th outside, and there should be an x there. But what I'm going to do now is look through, and I can't do anything to the sine to the 4th. I can't do anything with the cos right now. But again, 1 minus sine squared is another way that you can write your identity. So I'm going to rewrite this as cos squared of x. And let me pull everything back down, just like that. So now I'm just going to multiply everything through. So sine to the 4th is just what it is. Cos squared times cos, though, I can write s cos cubed, and the sign to the fourth is still there, which is actually equal to the left side. So even though they are in a different order because you're multiplying them, it's actually the same thing. So there you go, you've proved it.